If we look at the chain rule in one variable calculus, we look at the derivative of a composite function. So if we were to take the derivative with respect to x, this is denoted as, first we take the derivative of f with respect to u times the derivative of u with respect to x. You're probably more familiar with this as f prime of u times u prime, but this is just shorthand for this product of derivatives. When dealing with functions of more than one variable, we have a similar rule. Actually, there's more than one rule depending on the type of derivative we're taking. Usually it's helpful to write out a tree of dependencies. So for example, if z depends on x and y, and x depends on t, and y depends on t, we have a formula for computing the derivative of z with respect to t. The idea is we look at every branch that starts at z and ends at t. In this case, from this diagram, we've got two different branches, the one passing through x and the one passing through y. That means we're going to have two terms for our expansion according to the chain rule. So first, we've got this first branch, which is the partial of z with respect to x times the derivative of x with respect to t. So we write that out, dz dx times dx dt, plus the second branch, the one that passes through y, is the partial of z with respect to y times dy dt. So this is our derivative of z with respect to t. Now we can also have partial derivatives if the x and the y also depend on two variables. So the chain rule for that might look like the following. Z depends on x and y, x depends on s and t, y depends on s and t. So ultimately z depends on both s and t. So we can ask for the partial of z with respect to t as well as the partial of z with respect to s, because ultimately there are two variables involved. So we expand this similarly to the way we did the diagram up here. There are two paths that lead from z to s and two paths that lead from z to t. So for the partial of z with respect to t, I see we're going to go along this first branch from z to x to t. So that'll be the partial of z with respect to x times the partial of x with respect to t, plus the other branch, we're going to go along from z through y to t. So this will be the partial of z with respect to y times partial of y with respect to t. And those are partial derivatives. And the partial of z with respect to s works the same way. We expand along the first branch that goes to s. So this will be the partial of z with respect to x, partial of x with respect to s, plus the branch that goes through y. And this is partial of z with respect to y times partial of y with respect to s. So that's the chain rule for multi-layered functions of more than one variable. Let's actually see an example of this. Let's say we've got z is sine of x minus y, x is e to the t, and y is t squared. And let's say we wanted to find the partial of z with respect to, or the derivative of z, excuse me, because z ultimately only depends on t. So let's look at the derivative of z with respect to t. So first I see that z depends on x, so we've got the partial of z with respect to x, which is cosine x minus y, times the derivative of x with respect to t, which is e to the t. That's our first term, plus the partial along the y branch, which is negative cosine x minus y. That was the partial of z with respect to y, times the partial of y with respect to t, which is 2t. Now ultimately, this is supposed to be a function just of t, so at the end, we eventually need to replace all the x's with e to the t, and replace all the y's with t squared. So this gives us cosine of e to the t minus t squared times e to the t minus cosine x minus y times 2t. And of course, in this case, we can factor out the cosine. So we've got cosine e to the t minus t squared times e to the t minus 2t. Now in some situations, it may be easier to sidestep the chain rule and just plug in your subordinate functions into our function of x and y. So let's actually do this derivative in that manner instead. So if we look at dz dt, first Well, actually, first let's just write out what z is after the substitutions. So z is sine of x, which we have as e to the t, minus y, which is t squared. So now we go through and take its derivative, dz dt, is, well, we take the cosine, we take the derivative of sine, which is cosine e to the t minus t squared, times, by the chain rule, the derivative of the inside is e to the t minus 2t. So here's an example where it was actually much easier to do the substitution rather than doing the chain rule in two variables. There may be problems where it's easier the other way. So now that we have the idea of chain rule down, let's look at implicit derivatives. So implicit differentiation, we looked at pretty extensively in Calc 1, not differentiation. We looked at this pretty extensively in Calc 1. Here, it just gives us a shortcut using the chain rule that we've already developed. The idea is, say we've got a function of x, y, and z equals 0, and we're asked to find the partial of z with respect to x. So in here, implicitly, z depends on x and y. So in some sense, depending on the equation, you may be able to solve explicitly for z, but most of the time you won't. So the idea here is, if we take this equation and we take the partial derivative of both sides with respect to x. Well, first, looking at the left-hand side, f depends on x, on y, and on z. And z, we're implicitly assuming z depends on x and on y. So when we go to take our partial with respect to x, there are actually two branches. There's the one that leads straight to x, and then there's the one that heads through z and then to x. So we're going to have two terms for our partial derivative. So this gives us the partial of f with respect to x as our first term. That was along just the first branch, plus the partial of f with respect to z times the partial of z with respect to x along the second branch, and this equals 0. Now, what we're looking for is dz dx. So we just solve the equation for dz dx, and we see that dz dx, we go and move this term to the other side, so we get negative df dx divided by df dz. So if you want a quick way to remember this implicit derivative formula, this is the partial of z with respect to x is negative. Now these two are going to switch roles. Partial of f with respect to x divided by partial of f with respect to z. So the x that was in the bottom moves to the top. The z that was on the top moves to the bottom. So let's see an example of this implicit derivative before we move on. Let's say we've got x squared plus y squared plus z squared equals 9. And we want to know what is the partial of z with respect to y. So according to our formula, this should be negative partial derivative of f with respect to y divided by the partial of f with respect to z, where f is, well, we move the 9 over because our original equation had everything equal to 0. So minus 9 equals 0. So this right here is the f. We'll take its partial with respect to y, which is 2y. And we take its partial with respect to z, is 2z, and we reduce that, so our partial derivative of z with respect to y is just negative y over z. So we didn't actually have to do a whole lot of work on here. We just used this quick formula, and that gave us our partial derivative implicitly.